Okay, why don't we get started? Today we're going to go over a number of things, and we'll be deriving approaches and equations in more than one way, so you'll see things repeat a couple of times. But just to remind you, last time we introduced the idea of discrete time Markov chain, discrete time now. And we use this particular example whose transition probability matrix was given by that. And just to remind you of some of the terminology, this is the probability that the system finds itself in state j at time n. This is the vector of those probabilities. This is the limit of each of those probabilities. This equation 3 is clearly the sum of the probabilities going to 1, the conservation of probability. And this equation 4 is the way you find it. Basically, in equilibrium, the flow in equals the flow out. And so the probabilities of the last time to transition matrix lead to the same set of probabilities for the next time. We'll go over that a number of times today. This is the vector of those limiting probabilities. This, equation 5, is the vector version of equation 4, namely pi equals pi p. That's all about the equilibrium distribution. And it's a very important equation, pi equals pi p. We'll be referring to that over and over again. On the transient solution, the way in which these probabilities function over time, namely coming back to this second equation here, we know we can find at the time n from what happened at time n minus 1 into the transition probability matrix. And the solution to equation 6 is this equation 7. It's just an iterative argument to find the nth probabilities in time. You started with the initial probabilities at time 0 multiplied by the transition n times. And so if we can find p super n, we have a way of finding the probabilities as a function of time, namely this vector here. To do that, we introduced the z transform of these time-dependent probabilities and pointed out that I minus zp inverse, it has an inverse, which is exactly what we're looking for. And as our example, we ran that last time, we found p super n as a matrix with a multiple set of components, the first one of which was a stable matrix. It didn't depend upon n, and that was the equilibrium solution. And all the others decayed geometrically. And the decay rate were, in fact, the roots of the determinant. One of those roots is z equals 1, which leads to the equilibrium distribution. 1 to the n doesn't decay. Alpha to the n, where alpha is less than 1, does decay. And the rate at which the system decays was related to the product of the eigenvalues of that matrix. Okay, so that's where we were. I also introduced this rather interesting diagram. It talks about an arbitrary system of flow in which gallons of water are flowing into the system, coming in at a rate of f sub I gallons per second. And it exits at a rate f sub 0 gallons per second at time t. At any point in time, this system contains gallons, which we denote by capital F sub s of t. And we quickly wrote down last time this equation that the amount that's accumulated is the amount that came in from 0 to t, assuming it was empty at 0, less the amount that's left by time t. And this is talking about gallons of water, but we're going to use it to talk about probabilities. And this applies to anything. You could apply it to cars on a freeway, anything you like. And so it's a rather general, obvious equation. It's basically the conservation of flow. And if you like, we can draw a simple diagram showing what's going on in this gallons of water case. So let's plot versus the amount of flow, say x, we're going to plot the gallons in the system at time x. And let me first plot the amount that comes in as a function of time. And I'm going to draw an arbitrary picture here, supposing it looks like that. It can't decrease. The amount that comes in is just an increasing quantity with t. And so at some point, t, say right here, that doesn't work. At some point t, this is that integral. Whoops. This is that integral. Now at the same time I could plot, I've just plotted f sub I of t, and in particular it's integral, but the slope of this function is f sub I of t itself. The function itself, the curve, is the integral of that. Now I could also plot, say, the departure rate. The slope of this thing is f sub out of t, and the equation, the curve itself, is simply this integral here. And the difference between those two, this difference right here, is what? Well, I've told you what that difference is. The difference is just f sub s of t. So this difference is how much is in the system at time t. Now, if I want to talk about the rate of flows, I can talk about the rate of flow inside the system at time t. And that'll be the derivative of capital F sub I of t, which you already know is the little density, minus the derivative of the amount out. In other words, using a slightly different notation now, little f sub s of t, the rate at which this flow holding in the system is simply the rate in minus the rate out. This is a general equation. In other words, there's a time-dependent behavior for the amount inside the system, and that's what I call f sub s of t. The number of gallons in the system is changing in time, and the rate at which it changes is this f sub s of t. Now, I want to use this idea. I'm going to circle this equation. It's a rather important equation for general systems, and we're going to apply it right now to our Markov chain. So let's use it for our discrete time Markov chain. And let's consider some state j. Now, that state j receives probability from other states. And let's draw a bunch of possible other states. And I'll name them as I sub 1, I sub 2, down to, say, I sub p. And each of those is perhaps flowing some probability into this state J. From somewhere in this chain. And similarly, there's a set of states to which J is sending some probability because you're flowing from state J out there. Let's label those K sub 1, K2 down to K sub Q, say. So flows going out like so. And then we're going to say, look, let's consider the state J, the system I described up here. And I'm going to draw a circle around it. I'm going to look at the boundaries around that state. And I'm going to note that there's probability flowing in this picture. These input states are flowing in to J. These output states are flow out from J. And the system I'm discussing, state J, I'm going to call a system. Now, in equilibrium, the amount of probability flowing in is the amount of probability flowing out. So what stays in J is constant over n, over time. And let's look at the amount flowing in equilibrium. It'll be a sum on I of all those input states, pi sub I, times the probability of going from any one of those states into J. That's the flow in. And the flow out is whatever J had, pi sub J, times all the probabilities of flowing from J someplace else, over all possible K states, output states, of P sub JK. And of course, we have to append to this summation pi sub I equals 1. Now, what I've just written down is an equilibrium distribution. It's balancing probability. It says there's no change in the probability inside the system from step to step. So whatever flows in must be amount that flows out. Now, I'm going to get back to this same result in a number of different ways today, but I just wanted to give you an idea why intuitively it makes a lot of sense. Now, what I'd like to do is use that for the hippie example. So let's see if I have a nice picture of the hippie example someplace. There we go. And we'll see if I can capture this as I did last time. Great. Now I want to identify the three states of this system, 0, 1, and 2. And I'm going to use a color for each. I'm going to use the same kind of idea that I did in the top of the screen. I want to recognize each of those states as a system in which probability is conserved. So let's consider state 0 in red. Let me make it prettier. Let's consider state 1 in blue. And we'll consider state 2 in green, if we can find it here. Now, let's do this equation that I've written up here for each of those states. And the things I'm looking for are these equilibrium probabilities pi sub I. So let's look at the red state, and I'll write this in red. The red state says what? That what's flowing in? A quarter from pi 1 plus a quarter from pi 2, and that must equal what's flowing out of state 0, the red state, namely pi 0 times how much? 3/4 plus 1/4. Around the second state, the blue state, I could do a similar thing. What's flowing in is 3/4 from pi 0 plus 1/4 from pi 2. That's going to equal, out of pi 1, again, a quarter plus 3/4. And for the green state, similarly, state 2, I'm going to get what's flowing in is a quarter from pi 0 plus 3/4 from pi 1 plus from itself a half of pi 2, and that's got to equal what flows out from pi 2, which will be a quarter to pi 0 plus a quarter to pi 1 plus a half to itself. Now it's pretty clear that this self loop is going to cancel. It comes in and goes out. So you really don't have to consider it. It'll appear in a strange way as we go along. So I'm going to knock off this half here and this half here. You can eliminate the self loops, is what I'm saying. Now if you solve for this, what are you going to get? I mean, we can go through the agony of doing it now. It's just a little bit of calculation. Question? Okay. You ask, why is this 3/4 plus 1/4? If you look at this state here, what is happening? How much is leaving? Look at this picture up here. How much is leaving? And the answer is this 3/4 of it plus this quarter of it. That's where the 3/4 plus 1/4 came from.
Oh, the right side is the right.
Oh, the right side is what's coming out. Right. Okay. Now, if you solve for this, you'll be able to show, obviously, you get the same solution. But what do you need? What's missing? What other equation haven't I written down that you need? Excuse me? Right. The sum of all probabilities is equal to 1. We need that equation. So we also need the summation of pi sub I equals 1. Of course, there's a dependency, as we saw last time, among these, the red, the blue, and the green. Now notice, what I just did was a very easy way to write down the equilibrium probabilities equations. Just look at each state and balance it. What goes in comes out. So you don't have to have any fancy theory behind it and fancy mathematics. Just go down and write it out. Okay, so let's end with that example, and let's now make it a little more general. Let me point out that below is only going to be homogeneous Markov chains. It means that the Pij's don't depend upon time, don't depend upon n. And let me write down, so we're going to take a slight excursion now. Let's remember the m-step transition probabilities. We talked about that previously. namely going from I to j in m steps, is equal to, and by definition, the probability at time x sub n plus m you're in j, given that at time n you were in I. That's what we mean by the m-step transition probabilities. So let's see how that can work. Let me draw various states on the vertical axis and the time step on the horizontal axis. Remember, this is discrete time. And the state, the various states on the vertical axis. And let's look at, say, time n. Namely, I want to start off here and go from n to n plus m. So I'm going to go from n, and I'm going to work my way to some time n plus m steps further. Now, there's a whole bunch of states I can be in at time n, and let me draw a bunch of them. And there's a whole bunch of states I can be at time n plus m. And let me identify one of these as state I, and another one of these is state j, where I start and where I want to end up. And of course, there's some place in the middle, say here, at some time n plus q, where 1 is less than or equal to q, less than m. Some intermediate state. There's another place I could be, right? So let's draw a bunch of those. So if you will, this is an intermediate state. If I'm going to go from I to j, I got to pass through some intermediate state at time, through some state. So let's look at a bunch of paths here. For example, I could have taken that path, in which case I passed through state k, say, at time n plus q. Or I could have taken a red path, maybe a different way, but maybe also passing through k. Or another possibility, I could have passed through some different state, intermediate, or possibly even another different state. Always starting at I and ending at j. These are the sample paths I could have followed, okay? But I got to pass through some intermediate state. So let me write that down as an equation now. Let me say that if I'm going to go from I to j in m steps, it'll be the sum over all intermediate states, I'm going to call those k, to go from I to k in q steps, and the rest of the steps, m minus q, from k to j. And again, for the q I described between 1 and m. Rather obvious equation. You got to sum over all possible intermediate states. So there's a large number of these sample paths. This is basically a stochastic process. Goes to some place. Now I'm going to give an equation number to this. I'm going to call it equation 10. We may or may not refer to it later. But it's important, and it has a name. This is the Chapman-Kolmogorov equation, after the name of two people, Chapman-Kolmogorov. And we'll be seeing this over and over again. And this one was, for, as I said up front, for discrete time. Because I've implied that, let me say it exactly. So I'm going to write it out. For discrete time, homogeneous. Markov chain, which means the states are discrete. A Markov process would have continuous states, and continuous time would have continuous time. So there's 4 types, remember? Discrete time, discrete state, all the way to continuous time, continuous state. All 4 cases. Okay? Now in matrix form, this says the following. That P to the M, which describes the motions over M steps, is equal to the motion over Q tells the motion M minus Q. And this is for any Q in that range, 1 less than Q less than M. We're going to get to the continuous state shortly, but right now we're still with discrete state. Now I want to choose a particular value for Q. There's 2 important values. First of all, by choosing Q equal to M minus 1, right at the end, okay? Then that equation that I've called number 10 becomes P sub ij in M steps will be the sum over K, all the intermediate states, in going from I to K, Pik, in M minus 1 steps. And then the last step from K to J, that doesn't need a superscript. There's an implied superscript 1 step. Or if you will, P to the M equals P to the M minus 1 times P. And I'm going to give this equation a number. I'm going to call it 11. And make the point that equation 11 is a particular name. It's called the forward Chapman-Kolmogorov equation. And I'm going to refer to Chapman-Kolmogorov with the abbreviation CK. It's forward because it's the most recent time. Okay, or I could have done another similar thing. I can choose Q to be basically 1 at the forward end, at the initial time, the early end, which means I'm going to get Pij of M, again, is the sum over all intermediate states. At what time? First of all, it'll be from I to K in 1 step, and then you're going to go from K to J in M minus 1 steps. This is equation 12. And guess what this is called? It's called the backward Chapman-Kolmogorov equation. So I defined 11 and 12 with their names. It shouldn't surprise you to recognize that those 2, the forward and the backward equation, occur in far more than just queuing theory. You'll see that in other mathematical and stochastic process studies. So it's worthwhile for you to know that they exist and what they are. Very simple. It's a beautifully simple diagram here. Now I want to take a special case of discrete time homogeneous Markov chains. So let me draw a line here. I want to consider a special case of our discrete time homogeneous Markov chain. And the particular case I want is called the birth-death process. And basically what happens here is that the state changes by at most one. By plus or minus 1. And it models the behavior of a population. So, in terms of the physics, a birth increases the population by 1. And it's the population size that we're going to use as a state variable. A death decreases the population by 1. And we do not allow multiple births or multiple deaths. No twins, etc. We'll account for that later, if you will, in some of our models, but right now we're going to make it simple. So that means that the transition matrix will look like the following. With probability, which I'm going to denote by d sub I, j will be equal to I minus 1, d standing for a death. So in state I, you get a death probability di, and the state j becomes 1 less. With 1 minus bi minus di, j is equal to I, where bi, as you'll see in a moment, is the probability of a birth. So let's say that next. B sub I is the probability of a birth from state I, and then the next state is I plus 1. And there's no probability of anything else. You can't have multiple births or deaths. Now, it's not surprising that I'm going to require that d sub 0 be 0. You can't have a death when there's no one in the population. I mean, you could consider other kinds of models where that could happen, but for the example I'm using now, I'm using the intuitively pleasing statement, no deaths. In other words, no one can leave if no one is there. And similarly, b sub 0 is greater than 0. This is a little bit non-intuitive. You can have a birth when the population is empty. If you get religious, you can believe that, or at least for our model, we're going to say that. Okay? Because we have to get this thing started. If you started with an empty population, it'll be empty forever unless you have some births. Okay. So let's write down the probability transition matrix. And what I want to do is identify the state I and the state j values. So let me put them down here. Okay, so let's. And this is the matrix I'm drawing now. Okay, so what is the entry for 0, 0? What's the well, let's make it simpler. What will this particular entry be? If you have an empty situation in state I, and you want there to be 1 in state J an instant later, what is the probability that goes in there for the Pij? Excuse me? Bi, not quite Bi, B0, exactly. And there's no death, so what's the probability going from 0 to 0? You're in 0, and this next step, you're still there. No birth, which means 1 minus B0. And all these other entries in the first row will be zeros. Let's go to state 1 now. You start with 1. What's the probability you go from state 1 to state 0? Remember D0, 0? D1. 1 death. You had 1, you lose 1. Remember, you're going from 1 in the system to 0 in the system. You had 1, he dies, you have 0 left. This is pretty straightforward. And to go from 1 to 2 will be B sub 1, and from going from 1 and staying in 1 is 1 minus the birth minus the death. And all the rest are zeros. Let's do 2 now. Can you go from 2 to 0? 2 people? No, you can't, because at most 1 death. So that's 0. Can you go from 2 to 1? Sure. What is the value? Exactly. D2. And from 2 to 3 would be B2, and 2 to 2, neither a birth nor a death, etc. If you go to row I, you'll find at I minus 1, you need a death at rate I to go from I to I minus 1. To go from I to I plus 1, you need a birth, Bi, and 1 minus both of those to stay at the same state, etc. So it's a rather simple probability transition matrix. Sorry about that. Now, similarly, if the max population is some number, say n, then the nth row would be 0, 0, dot, 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 0, finally, dn, 1 minus dn, that would be state n, but you can't go to state n plus 1. There's no births allowed if the population is nailed at max n. So the birth rate stops. So that's the way you can handle that. So the point is that the birth-death system will give us pi easily. I mean, we pretty much see how to go up and doing that. Now I'd like to take a rapid transition into the non-homogeneous case to give you a sense of what's going on there, because some of these terms you'll occasionally see, or we may actually see it in this course as well. So I want to make a note now for the non-homogeneous Markov chain. Now, instead of taking the m-step transition probabilities and assume that they don't depend upon the time, as I set up here, this equation 11 said these probabilities, in fact, don't depend upon time. Now we're going to let Pij of m and n, going from state m to state n, will be defined to be the probability that you're in state j at time n, given you in state I at time m. And the intermediate states will be the states k at some time q, just like before, where now m less than or equal to q less than n. Now the Chapman-Kolmogorov equation well, we've written them down basically. Let me write them down again. Pij of m and n is the summation Pik of m and q times Pkj q comma n. It's not only the difference of these quantities, it's the values. It's not basically n minus q left over. Excuse me, m minus q left over. It's the q and the n depend upon exactly the values themselves. And the forward Chapman-Kolmogorov equation will look like this. It just takes a particular value for q, which means that Pij of m and n will be the sum when q is n minus 1. These sums are on k. P sub I k at times m and n minus 1, Pkj of n minus 1 n. Remember, the difference here from what I just showed a moment ago for the homogeneous is that I'm not taking differences, I'm taking absolute values of the time. And the backward Chapman-Kolmogorov equation will be similarly Pij of m and n will be the sum over k of p sub ik from m to m plus 1. Take one step out into the system, and then go from k to j all the rest, which is m plus 1 to n. The matrix form of that is simply that p at time n is equal to, I'm going to define what I mean by p sub I of n. It's a set of transition probabilities, Pij, at time n and n plus 1, one step. And remember, if it's homogeneous, if it were homogeneous, what notation do we have for p of n? It's the transition probability itself, namely p, without an n. P doesn't change with n. The Pij's don't change with n. Okay. So I'm going to define something. I'm going to define a matrix of these numbers here. It's a new definition. I'm going to call it a function h of m and n. And it's going to be defined as basically containing those elements, Pij of m and n. So these are the multiple step transitions. And h of n and n plus 1 is simply what we defined as p of n. In parens, if this was a homogeneous Markov chain, then h of m and m plus n would have been written as p to the n. But now we are depending upon the index itself. So we can write the Chapman-Kolmogorov here again. In general, in terms of this, will be h of m and n will be h of m over to q times h of q over to n. Again, m less than q less than n. What is h of n comma n? What matrix is that? Identity, exactly. It's that trivial case. Now, what we want to do, we'd like to find h, this funny guy h of m and n, in terms of p of n. If you look at the forward Chapman-Kolmogorov, you're going to find that the thing you're looking for, h of m and n, is h of m and n minus 1 times p of n minus 1. There's our old friend, just go one step in. And the backward Chapman-Kolmogorov is again h of m and n is equal p of m h of m plus 1. And n. Now I want to give an equation recognition for this first equation here. I'm going to just use a star. I won't need it much. I'm going to need it down below in a moment. Now, the solution to this equation, not a lovely form, but the solution is h of m and n is equal to a bunch of p's. It's a product of p's, just like we saw before, p to the n. It's p of m times p of m plus 1, p of m plus 2, dot, 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 out to p of n minus 1. So you're going to march there. What was the homogeneous Markov chain for that? It basically said h of m and n would be p itself to the n minus m. But the p's change with time, so we can't just use the same p. And similarly, the probabilities we're looking for, pi of n plus 1, the vector, will be the vector one time unit earlier times one step on the p matrix, which applies at time n. And if you work that out, we've seen this before, if you start at time 0, you go through a sequence of p's. P at 0, p at 1, out through p of n. This is very much similar to what we had the other day. Now this was for discrete time. Right after the break, we're going to look at continuous time. So let's take the break. get back to this now. Good. Having done that for discrete time, let's now do it for continuous time. Quickly. Let me Now we've got to go from this discrete model to a continuous model. So we're going to have to go through some simple shrinking of intervals. So for the non-homogeneous case, which is what we're looking at, we have the following. That going from I to j from time s to t is defined as the probability that your state variable at time t, x, is equal to j. Remember, it's still discrete state, but it's continuous time, given that at time s, you're in state I. And so the Chapman-Kolmogorov equation, no surprise, looks like this, that Pij of S and T is the summation over intermediate states again of Pik, going from I to an intermediate state k, starting at time s and going to time u, and then going from time u to time t, going from k to j. So it's Pkj u comma t. Matrix form of that equation is obvious, is H of S and T, which is defined as the probability. Well, it's just a set of values there. It's a matrix consisting of the Pij, S, and T. So in matrix form, the Chapman-Kolmogorov equation is that H of S and T is equal to H of S and U times H of U and T. And again, U is in between S and T. Now remember that for discrete time, not continuous time, we had the following, that this H function we had the expression that H of M and N was equal to H of M and N minus 1 times P of N minus 1. For the continuous time, we're going to let the time between discrete time intervals shrink to 0. So basically, we want to let the discrete time interval shrink to 0. So let's start with the difference equation and let it shrink. So what do we have? We had H of M and N was equal minus, want a difference now, minus H of M and N minus 1 is equal to, now what is H of M and N? Go back to that asterisk equation. H of M and N is given this way. And I want to use that now in my equation. So I'm going to write it this way now. That's H of M and N minus 1 times P of n minus 1. That's what I had upstairs. Minus the second term, namely matrix of m and n minus 1. And in matrix form, that right-hand side is simply h of m and n minus 1 times p of n minus 1 minus what? I need you to say it. Yes, minus the identity matrix. Okay. Now I want to make a definition now. Define P of t, this continuous variable, as a set of matrices, set of elements in this matrix, which are the Pij's of t and t plus delta t. And I'm going to let h of s and t be the limit of h of m and n as delta t goes to 0. So in some sense, we're going to let P of n, the time-dependent transition probability, it's going to basically go to P of t. So if you look at the equation on top of the page right now, I'm going to want to take a difference. As h of m and n gets shrunk down, remember, we're going to let h of s and t be the limit of this h of m and n as it drops down. So we're going to get h of s and t minus itself at t plus dt, delta t, I'm sorry, divided by delta t. That's going to be the partial of h with respect to t. So taking this equation at the top of the page, we're going to get the following equation. We're going to get the partial of h with respect to t as delta t shrinks to 0. Divide the whole thing by delta t and let it go. Will be itself h of s and t times q of t, a matrix, where q of t is defined as the limit as delta t goes to 0 of P of t minus the identity matrix over delta t. And this is for s less than t. This is called basically the forward Chapman-Kolmogorov equation. For continuous time. Q of t has a name. It's called the infinitesimal generator. Of this matrix of h, s, and t. Also called the transition matrix, transition rate matrix. and its elements are q sub I j of t, which in physical terms means it's the rate of going from state I to state j at time t. And what does it look like? Q sub ij of t is defined to be the limit as delta t goes to 0 of the pij over t and t plus delta t all of that over delta t. And this is for I not equal to j, because there's a special notation for q sub ii. And that's defined to be the limit as delta t goes to 0 of almost the same thing, but not quite. It will be obviously pii of t and delta t, pii of t and t plus delta t. But now we're going to subtract 1 from that and then divide by delta t. So in terms, qij, as I said before, qij of t is the rate of going from ei to ej at time t. From ei to ej at time t. And minus qii of t is the rate of leaving state ei at time t. And as a result of that special definition of qii, where you accumulate everything on the row of a matrix and put a minus sign on it, we're going to get the sum on any row, say j, of qij of t is equal to 0. And that's for all I. So it's similar to what we saw before in the discrete time. We had bi and di and the 1 minus bi minus di. We're basically taking 1 minus all the other terms in a row that are not on the main diagonal and putting that into the main diagonal term. Now, this was the forward equation. The backward equation is similarly the partial of h of s and t with respect to t is equal to minus q of s times h of s and t. And that's again s less than t, less than or equal to t. Now for the homogeneous case, we just did this for non-homogeneous continuous time. We get the following. That h of t, not s and t, but t, is defined to be h of s and s plus t. In other words, all you care about here is the time difference. If you remember, p to the m plus n power was equal to p to the m times p to the n. Similarly here, where P didn't change. Similarly, H is not changing. So all you care about is the length of time you're talking about, the interval. Q will appear, it's defined to be Q of T, and contains elements Qii and Qij. In the case of the homogeneous, then the Chapman-Kolmogorov equation looks like H of S plus T is equal to H of S times H of T. The forward Chapman-Kolmogorov says the differential of this H at time t with respect to t is equal to H of T times Q. And the backward Chapman-Kolmogorov is dH of T dt is equal to Q times H of T. And once you've got that in the homogeneous case, the solution, this equation, is that H of T, no surprise, is e to the qt, a matrix equation. No surprise an exponential comes in when you see either of the two equations above. That almost smells like an exponential, and it is. And the state probabilities? D sub pi j of t now, with respect to t, is equal to qjj times pi j of t plus the sum for k not equal to j of qkj pi k of t. I'm going to call this equation 13. And in matrix form, it's simply that the derivative of pi of t is equal to pi of t itself times the infinitesimal generator q. Now, further on, for the continuous, irreducible, homogeneous Markov chain, we get the following: that pi times q, pi the vector, times q is equal to 0. This is the equilibrium distribution we're asking about. This, along with the summation of the probabilities going to 1, as always. And this is similar to what we started out today with, to pi equals pi p for discrete time. So we've gone all through this continuous time material, non-homogeneous and homogeneous, to get to an equation like this pi q equals 0, limit for continuous time. Okay, now all that I said once I went to this continuous time is a kind of excursion. Okay, I want you to understand there's some deep theory behind it all. I'm not going to hold you responsible for being able to reproduce this, but I want you to know it's there. There are models similar, all Chapman-Kolmogorov equation models for the continuous time, for the non-homogeneous time. Okay. So having said all that, I'm going to draw a line. should make that in black. And I want to go back to the birth-death processes now. We took an excursion. Now let's continue the birth-death process. Now, we know for birth-death that from some state EK, you can only go, remember now this is discrete state, you can only go to what states in one step in time, discrete time again, okay? Where can you go from state K? +1, -1, or back to itself. You may go nowhere, okay? So you can go basically to EK +1, itself, EK, or EK -1. And what we're going to do now in our calculation is we will get an explicit solution here. So this particular example, birth-death process in discrete time, allows us to get an explicit solution. And in some cases, people begin queuing theory right here. But in fact, what I want to do is I want to now go to continuous time. We can actually handle that case, since we've set up some mechanism for it. So what we're going to do now is study a continuous time discrete state homogeneous birth-death process. Now you already have an approach, even if I didn't say birth-death process. Way in the beginning of today's lecture, I talked about the flow of gallons and all, and rates in equal rate out, and the difference between those is the rate at which things grow in a state. You can write down the equations just by drawing circles around the states and saying the flow in minus the flow out is what the flow that's accumulating. But once we go to birth-death process, which is a special case of a Markov chain, then we can get an explicit solution. So what we're doing is we're talking about nearest neighbors only. Now, once I go to nearest neighbor, Artie, I'll get back to what you said. What does it mean to return to a state in continuous time? If you're in a state, you're waiting for a birth or a death, say, you're constantly returning to yourself over time. Every delta t, you're going from 10 people to 10 people to 10 people, a birth, now you're 11. So you're cycling around infinitely quickly, but you're taking out and putting in the same thing. So you basically tend to ignore that, and that's why the QII we defined earlier was special to contain that case. I want to give you a heads up as to where some of the physics of the system goes. So nearest neighbor only. So I'm going to start off by defining the following. I'm going to define not the probability of a birth in discrete time, but the rate at which births occur in continuous time. It's called a birth rate. And we're going to call that lambda sub k. birth rate in state K. Namely, when the population size is K. And a death rate, I'm going to define it as mu sub K. Now understand, we're going from discrete time to continuous time. In discrete time, it was a probability of a birth in the next step, probability of a death in the next step, probability of nothing happening in the next step. Now we're talking about the rate at which it happens in continuous time. So many, you get a birth at a rate of 10 children per second. Okay. And again, as I say, much of queuing theory begins with this very simple model. You saw the example of the hitchhiker, which was discrete time. Every midnight, something happens. Now, every instant, something can happen. So in some sense, I'm going to remind you, or just point out, that lambda sub k that I just defined is what we called q sub k comma k plus 1. It's the rate of going from state k to state k plus 1. And mu sub k is q sub k comma k minus 1. And q sub kj is equal to 0 for the absolute value of k minus j greater than 1. But remember, the qkk was that special thing where you subtract the stuff out. I want to identify that now. We required that the summation of the qkj of all possible next states was equal to 0. So that means that q sub kk must be the negative of the other rates when they were k, namely it'll be minus lambda k plus mu k. In other words, it's equal to minus the rate of departure from state K. Remember, this is homogeneous, so the time doesn't matter, just the fact of moving between states. So let's draw the Q matrix. So again, I'm going to do this. I want to label the rows and columns. I'll do that in red just to distinguish them. This is row 0, 1, 2, down 3. Similarly, this is column 0, 1, 2, 3, etc. And now I want to write down this Q matrix. So let's take a simple one. What's the rate in going from 0 to 1 in terms of notation above here? Nope, nobody in the system, 1 birth in the next instant of time. What rate is that happening? Nobody in the system. What's the rate at which you get births? Lambda 0. So that's what I'm going to put down here. Anything else in this row have a value? 0. What's the value under 0? Let me give myself a little more space. I'm going to relabel these to give me double space. But keep thinking about the question I asked. Let me move this over. We just identified this term to be, lambda 0. What are the other terms in that zeroth row? Yes? Not 1 minus. The suggestion was that this quantity here is 1 minus lambda 0. But no, lambda 0 is not a probability. It's a rate. And remember, right here, that the sum of the rates on any row is 0. So what should this element be? Minus lambda 0. All these others are 0. You can't go to higher number states when there's nobody there in delta t seconds. I'm seeing quizzed faces here. Nobody in the system. At what rate do you go from state, do you get a birth? Lambda 0. That's what this meant. Up at the top of the page. There's no deaths because there's nobody to begin with. Now, when you're in state 1, at what rate do you go, say, to state 2? Lambda 1. You can't go any higher, so this is going to be zeros here. What else can you have in this row? Yeah, you've got 1 in the system, so you could have a death. Okay? And if you have a death when you're in state 1, where do you go? To state 0. And what rate do you have a death when you're in state 1? Mu1. So that's going to be right here. And the on-diagonal term, we said, has to sum to 0. So this is going to be our friend minus lambda 1 plus mu1. And all the rest of these are zeros here. Yes, question. It's basically there to account, to force this to be a row summing to 0. Okay? Because 1 doesn't mean anything. These are rates, not probabilities. So I don't want them to sum to 1. That wouldn't mean anything. And I don't want them to sum to infinity. And don't forget, I've got this pi q equals 0 term here. I forced all of this back here to basically consider the, it's a definition, okay? But it when you work with it, it intuitively makes sense. Okay, and the mathematics works that well, but it's I can't give you a physical interpretation. But it certainly is not going to sum to 1 or minus 1 or something. These are rates, not probabilities. What it really is, if you wanted to put a true rate on the diagonal, it would be infinity. If you're in some state, the rate at which you're going back to that state is infinite. You're cycling around. And that's meaningless. So we use something else for that term. We force the rows to sum to 0. Okay, let's do 2 now. 2 is going to put me a lambda 2 from 2 to 3, a mu 2 from 2 to 1, and minus the sum of those two on the diagonal, and 0 everywhere else, etc. Okay. So I'm going to write some more notation down now. So the assumptions for our birth-death process are the following. First of all, it's a homogeneous continuous state Markov chain. On the states 0, 1, 2, etc. Assumption is that births and deaths are independent and that comes basically from the Markov property. And it is a Markov chain we're talking about. And now some notations. The assumption B1 is that probability of exactly one birth in the interval t comma delta t is equal to lambda, given k. Let me add the given k. Need some more space here. Given there are k in the system is equal to lambda sub k delta t plus little o of delta t. And what does little o of delta t mean? It's a quantity that goes to 0 faster than delta t, our usual notation of small o. Okay. D1, same thing, probably exactly one death, given the same thing, is equal to mu sub k delta t plus little o of delta t. B2 says that the probability of 0 births etc., given k, is equal to 1 minus lambda sub k delta t plus little o of delta t. So the first order, it's 1 minus lambda k delta t. And D2, similarly, probability of 0 deaths is equal to 1 minus mu k delta t plus little o. What do we want to solve for? This quantity p sub k of t, which is the probability, as always, that at time t, the state you're in is k. The time t, there were k in the system. Now we're going to show an easy way to do that, by the way. Notice I've made a slight change of notation. Note, I'm using p sub k of t here to represent what I called pi sub k of t before. It's a notation change, because I want to use pi was for general Markov chains, and the capital P I'm going to use for my particular queuing systems. So I'm going to use the CK approach, the CK dynamics, talking about the intermediate states. I want to see what happens to populations at time between time t and t plus delta t, obviously. That's what we're going to do. And we'll end up with EK if one of the three things happens. Suppose we're in K, okay? how did we get, well, not where we started out, but how did we end up in state K? Either we had K at time t, and no state changes, in this interval t plus delta t. Or we had k minus 1, one too few, and we had a birth in this interval t plus delta t. Or similarly, we had one too many, and we had a death. So to draw that as a diagram, if I look at the state EK, I could have gotten there from EK plus 1, or from EK, or from EK minus 1. And to do that, from EK plus 1, I needed a death. From EK, no changes. And from EK minus 1, I needed a birth. That's the only way I can get to EK in next delta t. And what I'm showing here, in some sense, I'm going to lay a time axis on that picture. And say that this point in time is t, and this point in time is t plus delta t. So let's use the things we've learned and write down the equations that matter. What's the probability that I'm in state K at time t plus delta t? It's equal to the probability that at time t I had K, and I went from K to K in delta t. Or I was in state K minus 1, and I went from K minus 1 to K in delta t. Or at K plus 1 at time t, and I went from K plus 1 to K in delta t, plus little o of delta t. Other things could have happened at an extremely small probability. And this is good for K greater than or equal to 1, because I allowed myself to have to go down from K to K minus 1, or come up from K minus 1 to K. For K equals 0, there's a similar, slightly simpler equation. We get P0 of t plus delta t equals P0 of t times P00 of delta t plus P1 times P10 of delta t plus little o of delta t. Namely, I could not have had a death starting from 0. Now those are the equations, but I need one more equation, and we always will know what that is. The sum of the probabilities has to go to 1 at any time. summation of pk of t at any time. Oh, okay, must go to 1. Okay, so let's look at that top equation and let's plug in, because I know what these pkks and pk minus 1s are all about. That's up here in these b equations, the b's and the d assumptions. So let's write it down. You can do it by inspection. I'm going to get p sub k of t plus delta t, this first equation, is equal to probability I was in state k at time t, and first of all, I didn't get a birth. That's 1 minus lambda sub k delta t plus little o of delta t. And I didn't get a birth independently, so I multiply these probabilities. 1 minus mu sub k delta t plus little o of delta t. Again, I'm multiplying those two events because they're independent probabilities. Oops. Plus the other case, pk minus 1 of t times, now I need a birth. What's the probability of a birth? Go back up to my assumptions here. That's b1. It happens lambda k delta t plus little o of delta t. Lambda k delta t, little o of delta t. Or I could have had one too many, pk plus 1 of t, and then I need a death. That happens with probability mu k delta t plus little o of delta t. And for the 0th term, p sub 0 of t plus delta t, I'll get a similar set of equations. I'll get p0 of t. This time just no probability of a birth, so it's 1 minus lambda sub 0 delta t plus little o of delta t. Or I could have had one too many, and I get a death. And that's going to be simply mu1 delta t plus little o of delta t. Plus, as always, little o of delta t. Something else could have happened with infinitesimal probability. So let's expand these equations now. In other words, in this first equation up here, this one here, expand that factor, this factor here, etc., because you're going to multiply these guys together. Okay, so let's do that. I'm going to get that p sub k of t plus, I'm taking you through this all this torture for a good reason. I want you to feel how cumbersome it is. Because when you're all done, I'm going to show you how to do it like that. So you'll appreciate it. Okay, so let's suffer a little bit. Expanding that first term, I'm going to get pk of t times 1. That's this term here. This times that. That 1 times that 1. Minus lambda k plus mu k times delta t pk of t. You're going to get saved by the bell. And later on, I'll add the O of delta t. There's an O of delta t that's going to contribute. Plus, coming down to this next term, this one here, I'm going to get a lambda k pk minus 1. This equation up here, I missed a subscript, I'm sorry. In this equation, there should have been a lambda k minus 1. So please put that in. A birth from one state too small. Nobody caught me. Okay. Plus, here comes that lambda k minus 1 times delta t down to pk minus 1. Plus, the last one going to give me mu k plus 1, delta t, pk plus 1 of t, and all the little o of t's, I'm going to add all in just one of them. And I shouldn't keep you longer than you allotted time on a Friday night. So we'll stop here. We'll pick up in the next class, okay? You can finish this yourself. Try it and play with it. Suffer a little bit. And then you'll appreciate where we're going. So next class, Monday. Now, as I mentioned to some of you, I've already assigned the third assignment. It's due a week from today. So you have another assignment. Assignment 2 is due the end of the weekend.